Excellent. Okay. Hi, I'm Dave McGaugh with the Pacific Northwest Gigapop. Today I'll be talking about Pacific Wave and our foray into hybrid exchange services. I've got a few new terms that I'll be introducing. Pretty common in the research and education community, might be new for some folks that aren't as closely involved. So real quick about Pacific Wave. It's a joint project between the Corporation for Education Network Initiatives in California, some folks know as CNIC, and the Pacific Northwest Gigapop in cooperation with USC and University of Washington. It's a distributed internet exchange point running up and down the West Coast. Supports high-end network protocols, IPv4 unicast multicast, IPv6 unicast multicast, and then jumbo frames in any combination there. So some of the initial Pacific Wave services are pretty traditional to exchange points, except for that it's done in a distributed manner. So provide an open infrastructure for connecting international IP networks, which is our primary focus across the Pacific Rim. Facilitate any-to-any connectivity between the connectors, and then we are able to do this without involvement of the exchange operators with the shared VLANs, and I've got a kind of a diagram that depicts some of that. And then we do have private VLANs that we can provision for participants on an as-needed basis. So this is kind of a picture of the international participation in Pacific Wave. So as you can see, our real focus is to provide an interconnect point for all the, primarily the research and education entities throughout the Asia-Pac region. And those connectors come in at anywhere from OC3 speeds to 10 gigs or multiple 10 gig connections. And then also provide kind of a meet point for the research and education networks in the US and connectivity into Canada and Latin America, which was added fairly recently. So some of the characteristics, again, the distributed connectivity with the shared broadcast domains. With the shared VLANs, we have a pretty strict connector policy to make sure that nothing strange happens on the VLAN. So we restrict single MAC address per VLAN with port security. Have a policy of not allowing connectors to do anything other than connect layer 3 devices directly and do things like spanning tree root guard. So this is a diagram of the shared VLAN infrastructure. So basically there's a notion of local VLANs and intersite VLANs. So the intersite VLANs are where connectors in the same geographic region connect. So for example, two Seattle participants might peer across the local VLANs. And then if a Seattle participant and a Bay Area participant wanted to connect to each other, then they would actually peer across the intersite shared VLANs. And then take all of those and overlay that with a jumbo MTU variety to allow jumbo peering. And that's, given the research and education focus, we have a pretty big focus, concentration on the jumbo MTUs. And I would say that probably the majority of the peerings that take place across Pacific Wave are jumbo enabled. So this is the physical topology. There's nothing too fancy going on here, actually. So it's 7609 in Seattle in the Weston building that rides a 10 gigabit LAN PHY Lambda on National Lambda Rail facilities down to Sunnyvale, and lands on a 6509 in the Sunnyvale Level 3 facility in the National Lambda Rail colo space there, and then a 10 gig connection over to PAX Palo Alto, and then 10 gig connection on scenic facilities down to one of the Equinix facilities with a 10 gig connection over to the other Equinix facility in LA, and then a connection over to Wynn Wilshire. So that's kind of the peering services and some of the natures of the traditional layer 3 interconnect services that Pacific Wave has offered and continues to offer. So over the last couple of years, we've seen a pretty large uptake in the R&E community, and kind of hybrid networking is one name for it. So basically the idea of being able to have these light paths, as they're called, and I've got a fairly good definition of that, I think, on the next slide. So these light paths that allow researchers' labs to interconnect with one another to do whatever they, move whatever traffic they choose over it without the involvement in any layer 3 networks. So our first use of that was at the iGrid 2005 conference, which was at UCSD in the fall of 2005. And there we had over 10 gigs of additional bidirectional traffic on top of what the exchange was already carrying of normal production peering traffic, including 3 gigs of multicast, which was generated out of the University of Washington. Those were, I believe, 4 750 meg multicast flows that we were replicating with pin snooping in the switches. For the iGrid support, we added a couple additional shared VLANs, and we're using some of the production shared VLANs, and then added some additional private VLANs for some of the Lightpath extensions. So we had connectivity. In some cases, we had layer 2 domains that originated in Korea, came through Seattle, and all the way down to San Diego, and landed on some equipment that we had in the UCSD facilities. And then, so a lot of the private VLANs that we were able to create, we just put up basically for the conference and then tore them back down. So this kind of got us in the habit of this is the sort of services that we can provide for kind of some of the non-traditional connectivity needs for the researchers. So this kind of got us thinking on how we can kind of start to do this more often in a more scalable fashion. So Lightpath, this is one of the pretty common terms that's used in the research and education community today. So it basically defines a more or less a layer 2 connection from one point to another, no routers in between. Doesn't necessarily define the protocol which underlies it. So in some cases where Lightpath may be a traditional switched Ethernet connection or MPLS layer 2 VPN. In other cases, it may be like a 10 gig lambda over a WDM system, or another thing that's quite common now is that the community is pretty much agreed upon GFPF as the encapsulation method to run Ethernet over SONET. So a lot of Ethernet over GFPF frame mapping type services. So this is actually what the kind of a high level of what the network topology looked like for the iGrid demo. So on the right vertical line is the normal production 10 gig lambda that we have between the nodes in Seattle, Sunnyvale, and LA. And then the 2 vertical lines to the left are 10 gig lambdas that we put in place over NLR and scenic facilities to augment the connectivity. So we had one connection that went out of Seattle and straight down into the San Diego equipment, and then another connection that kind of just bypassed Sunnyvale. And then all the international connectivity came in through Seattle. So we had the CreoNet 2, which is the Korean higher ed network, came in at 10 gigabits per second. We have a circuit from Tokyo that we cooperate, that Pacific Northwest Gigapop and WIDE cooperate and operate to carry traffic across. And then GemNet, which is another one of the higher ed networks in Japan that is operated in cooperation with NTT, had a pretty large connection coming in there for some super high def stuff they were doing. So some of the administrative leaps that we've had to make from being a traditional exchange facility to a hybrid exchange is perhaps relaxing some of the connector policies. So if we're carrying these layer 2 domains from basically around the globe, then obviously the policy that says that you can't connect direct layer 2 devices doesn't really work in that sort of situation. So deciding how to handle that. The other thing is if we're doing the private VLANs and not relying on everything for shared VLANs, then we as the exchange operators have to act a little bit more quickly, perhaps to some of the provisioning requests for the private VLANs and things like that, because some of the demos and experiments that some of the researchers are doing have a little bit less advanced warning. And then, haven't done anything with this yet, but whether there's additional billing models that should be considered. So Right now, the billing models are fairly similar to all the internet exchanges that you're familiar with today, whereby you basically pay for the port fee and do whatever with the port you choose, and move as much traffic across it as you choose. So technically, though, again, definitely seeing an increased use of the private VLAN so that we can basically provide a private end-to-end connection or Lightpath through the switch fabric that may originate on one side of the globe and end up on another side of the globe. And then less controls over what types of devices. So we may see a connector come in with another layer 2 switch. We may see them come in with a L2 VPN over their layer 3 network, or may come in over like a WDM Lambda or something like that. And then the other thing that that's definitely been a challenge is when we're connecting the native layer 2 devices is trying to avoid VLAN ID collision. So like right now today, we have probably 3 fairly permanent connections to other layer 2 networks. So what we've had to do, those ones that we know that we connect to regularly, we've been able to kind of set aside VLAN ID space that we know doesn't overlap with each other, and we know that we can always go back to that range and ensure that there's not going to be any issues. But as we kind of chain these layer 2 domains together, then it becomes quite a challenge, because it may not be the case that the VLAN ID space that that Pacific Wave and perhaps another exchange have agreed upon may not overlap with the next hop of layer 2 domains. So some of the realities: the light paths are not provided by the same end-to-end technology. So ideally, in some cases, if the researcher has the need for some sort of layer 1 GFPF mapped frame mapped service, the likelihood that that's going to be able to be provided end-to-end can be pretty challenging sometimes. So in some cases, you may have what starts out as a GFPF frame map service, comes out of the researcher's lab, goes into a traditional layer 2 network, maybe across the MPLS domain, and then back out to another traditional layer 2 network. So one of the things as an hybrid exchange operator that we are trying to fill is kind of act as, in some cases, that translation point. So if we have all the different devices in the toolkit, then we can provide that interconnect between the networks as necessary. So kind of the layer 1 infrastructure that we're able to offer. In Seattle, we've got a Nortel HDXE that we cooperate with Canary, which is the higher ed organization up here in Canada, actually. And they actually cooperate a number of HDXEs along the kind of the northern tier of the U.S. And then we also have a Cisco 454, which is populated with 4 of the ML1000-2 cards. So that allows us to do GFPF or LEX encapsulation in cases where we have connectors that aren't able to do GFPF on the older Cisco cards, for example. The ML cards do support RPR, but we don't really see much uptake of that across the wide area. So it's basically the GFPF that most people are focusing on. And then the Koreans also operate a 454 that's part of the Seattle node that allows them to do some direct connection through Korea, and they have a 10 gig connection that lands on that. And then in Los Angeles, there's a 454 that comes in and terminates the 10 gig connection from ARNet in Australia via Hawaii, and that's broken out into 8 giggies that's GFPF mapped. And then also a 454 that's breaking out once again into the 8 giggies and actually terminates on the Nortel HDXE up in Seattle via an OC192 over National Lambda Rail and scenic facilities. So this is kind of the picture of the combined layer 1 and layer 2 equipment that Pacific Wave operates. So you can kind of imagine as you interconnect these devices in various points, then you can kind of build whatever's necessary from any network to another network via whatever protocol translation you have. So as I kind of alluded to before, the supported Lightpath types On kind of one end of the spectrum, the Ethernet frame map services. Things like no stat muxing, obviously, when you're talking TDM, but we have predictable jitter and latency. And then on the switched Ethernet side, one of the advantages is the ability to hand off a 10 gig convenience interface. So to date, when we're talking about 10 gigabit light paths, on kind of the layer 1 service, we can either hand them a dedicated 10 gig lambda or not. The switched Ethernet provides us the ability, for example, if a researcher wants 3 gigs of traffic or something like that, then we can provide them a 10 gig handoff, but still not have to burn an entire 10 gigs worth of transport. So obviously, though, when we're talking about frame or packet-based networks, then we may end up with additional concerns for frame loss when we're running congested links or backplanes or anything like that. And then there's a bit of debate whether this is truly a light path, because one of the things that the light path defines is something that's very predictable, has very predictable performance characteristics. So again, one of the things that as a hybrid exchange operator, we're providing kind of that layer 1 and layer 2 interconnect while still maintaining the traditional core services of providing a fabric for the layer 3 networks to peer with one another. Today, that layer 1, layer 2 translation we're doing with manual physical cross connects between, for example, Cisco ONS and the Ethernet switches. In the future, though, a lot of time is being spent on optical, like white light switches that we would be able to connect the boxes together, and then ideally, in the fullness of time, be able to control all those via some sort of control plane policy protocol like GMPLS or something like that. So there's actually a lot of work being done in the community with those sort of things, and actually some inter-domain controls for some of the GMPLS networks. So when we have researchers that are asking for light paths, some of the technology choices that are taken into consideration are what are their performance requirements, their bandwidth requirements, and time frame that they need the service activated. So in some cases we can provide, for example, a switched Ethernet a lot faster than we can free up time slots on a TDM-based solution. And then, of course, the availability of the wide area transport. So especially going across the Pacific, we may only have something that's configured as a layer 2 offering, and it would be pretty difficult or service interrupting to reconfigure that. So Pacific Wave's involvement in glyph. So this is a pretty common term in the R&E community, but probably a new one here. So glyph is the Global Lambda Integrated Facility. I've got some URLs at the end that you can actually read a little bit more about some of this stuff. So the whole idea here is that it provides basically the ability to have these light paths from one lab to another on kind of a global scale. And that's actually, it still takes in order to put some of these pretty complex light paths together, the way that this is done today is via a pretty long email thread, but it actually works pretty well once everything's put together, and it's not uncommon to find these light paths, these layer 2 connections that stretch from literally one side of the globe to another through various goals. So the goal, Pacific Wave is a goal. This is a glyph open light path exchange, so it's basically the idea of an exchange point specifically for interconnecting these light paths. Some other examples of goals that are part of the glyph are KR Light, which is in Daejeon, Korea, another light in Amsterdam, and HK OEP, which is the Hong Kong Open Exchange Point in Hong Kong. So one of the things that Pacific Wave does is it kind of introduces this term of a distributed goal. So as I kind of mentioned before, the Pacific Wave is a distributed exchange point that kind of provides the any-to-any connectivity regardless of which nodes participant connects at. So we're kind of attempting to do that with the light path exchange as well. So being a distributed goal, some of our properties are that we're able to provide kind of the any-to-any connectivity, the protocol translation in some cases, so have the different technologies in our toolkit at all the locations up and down Pacific Wave. And then the other thing is kind of on more of from the administrative standpoint is we see Pacific Wave as a single entity, so we are able to deal with participants that connect to the exchange as though we're a single entity, even though we kind of cooperate the devices between CNIC and Pacific Northwest Gigapop. And then ideally what we'd like to be able to say is that we have no bandwidth limitations between nodes. So if you can imagine that if Pacific Wave was not distributed and was in a single location, then we'd be able to provide the connectivity between all the various equipment so long as there were ports available and fiber. And we want to try and be able to do that across the wide area. And of course, this is within reason. We do have a pretty good access to 10 gigabit lambdas up and down the West Coast, but at some point we do run out. So we try and use those in as intelligent manner as possible. So one of the things that the glyph tries to do is actually define a kind of a high-level way of representing connectivity between the various goals, and this is what you see here, the idea of these circles and clouds, and this is the Pacific Wave's version of that. So as you can see, the Pacific Wave at the various points has connectivity to the KRLite, the TLEX exchange in Tokyo, CSTNet in Hong Kong, connectivity, as I mentioned, through Hawaii to ARNet, and then connectivity to ManLAN in New York, and actually fairly robust connectivity to Starlight in Chicago. So some of the future technologies that we're looking at, today Pacific Wave's a traditional layer 2 switching fabric, linear interconnects, 10 gigabit connections. Some of the things that we've been looking at in the future, though, are more complex wide area topologies. So, if we can provide some redundancy other than that single connection that runs up and down the West Coast, and also if we want to have some sort of additional bandwidth management, then things like MPLS layer 2 VPNs become a little bit more interesting to provide, let everything run underlying on a layer 3 network to have a little bit more control over, if we're doing like RCPTE or something like that, to control the actual pathing of the layer 2 connections and then have some sort of redundancy between there. And then also optical switching between the connections. And then some of the other upcoming technologies that we're kind of keeping an eye on. GFPF 10 gig LAN PHY. So basically the notion here is potentially be able to do the same thing that we're doing with Gigi. So for example, it's not uncommon for us to be able to provide a Gigi that's in fact mapped over like a 622 meg time slot. If we could provide a 10 gig handoff the same way, but maybe is mapped over like a 2.5 gig time slot, then we can provide the 10 gig convenience interfaces but not burn the entire 10 gigs of bandwidth across a wide area connection. The reason that in some cases we're looking for some sort of greater than 1 gig concatenation of services, but something less than 10 gig is we have, it's not uncommon to find really large flows of traffic, so it's pretty common for us to be able to generate 750 meg flows, and in some cases greater than that. So once you get up to that, those size flows, then relying on some sort of load sharing algorithm for link bundling is not something that you want to put a lot of faith in. And then as we're interconnecting the various layer 2 facilities, have some more robust VLAN tag rewrite capabilities. So we can kind of accomplish some of these things today with MPLS L2 VPNs depending on the device that we're operating it on. And then this is some URLs that I have here. If nothing else, then it should be in the on the website if people want to go back and read a little bit more about some of this stuff. One thing I didn't mention in the presentation is this thing called network description language. So there's a lot of work that's happening in the glyph community as a way of kind of, so they have the agreed upon way of kind of displaying the interconnect between the different glyph goals. There's some work that's being done to have kind of a standard way of actually defining the resources that are available, and then at some point actually be able to do something more interesting with that, as far as perhaps doing some automated provisioning or something like that. So University of Amsterdam's been doing a lot of work with NDL, and at some point Pacific Wave should be publishing its own NDL, although it's something that I haven't quite got around to yet. And then National Lambda Rail is the infrastructure that Pacific Wave relies on in a lot of cases. And that's all I have.
Are there any questions for Dave? Well, I have a question, but while I'm asking my question, could Niels, the next presenter, get up here with his laptop, because he's using Keynote, so we need to get him up here. I really thank Dave for coming in and submitting this presentation, because Pacific Wave was always one of these sort of enigmas to me, of this wide area distributed exchange platform operating across multiple administrative domains, and I was thinking, how the hell do they get this to work? So I think, you know, one thing that's interesting, I said to you, was like, where's the funding coming from? So, I mean, do you want to just say a couple of things about that?
Yeah, so basically the way it works is the Seattle node is actually a piece of equipment that's owned by Pacific Northwest Gigapop, and Pacific Northwest Gigapop puts its resources into that node, and then CNIC invests the capital into the equipment in California. The port fees on Pacific Wave are basically on a cost recovery basis, and in fact, from a peering perspective, the port fees are dirt cheap. I believe, I can't remember exactly, but I believe a 10 gig port is like $1,000 a month. But one of the things in the agreement is that the participants that peer on Pacific Wave agree to peer with Pacific Northwest Gigapop and CNIC, so it's kind of acts as a bit of a cost recovery model there. But there's a lot, the cost recovery model is probably not exactly perfect, but it's basically the Pacific Northwest Gigapop and CNIC's dedication to ensuring that there's good connectivity up and down the West Coast for the international networking.
Okay, and we have a question on the center from Avi.
You mentioned that you don't allow layer 2 devices to connect, but you also mentioned the VLAN tag issues. So I assume what you're saying is most people connect like Catalyst devices that are sort of layer 2, sort of layer 3.
Yeah, and that's something that's, I guess, has become more popular in the last couple of years, is the devices have become more practical to use as internet routers. So it's kind of a fuzzy area. The only thing we can ask at this point is that they configure the devices as basically a routed interface versus a switched interface. But it's kind of, I guess, and this is probably an issue for all the exchange operators, is it kind of puts them in a difficult situation, because they want to allow people to connect with reasonable routers that are fairly inexpensive, but at the same time they don't want anything crazy happening with their exchanges. So what we've tried to be able to do is just do the MAC address limiting with port security, and hope that catches most of the oddness that goes on there.
And the second question, I think I saw you addressing a little bit, and it's related to the first question actually about VLAN tag translation. The catalysts that you're running support some amount, it's only like 128 per ASIC of VLAN translation, and then there are other platforms that do VPLS, VLL, which also help you with scaling, because now you're not limited to layer 2 for multi-trunking and going between switches.
Right.
Have you played with the Cisco, or you just say that's not scalable enough for us to actually build on?
So to be honest, we've actually been able to avoid any VLAN tag rewrites so far. The issue of, I believe the way that Cisco works is everything on the same ASIC has to use the same rewrite functionality if you want. So I think one of the things that hopefully may alleviate some of this is if we do decide to migrate to MPLS L2 VPNs, then then, to at least to some extent, it becomes a little bit more of a port-specific, port-unique type of VLAN ID setup. So.
Okay, thanks. Any more questions? Yeah, I've got one more question.
Hi, Virendra with the 86 Technologies. You touched on the spanning tree root guard. How are you guys preventing spanning tree storms? In other words, are you guys playing with the root domain with the roots, or
No, to be honest, the spanning tree deployment is not terribly sophisticated that we have right now in Pacific Wave, and so basically, and in fact, the Seattle node and then the California nodes actually operate separate spanning tree domains because technically the California-based devices are actually, we cooperate them with Scenic, but they are actually they have the provisioning control of those. And so they are kind of act as somewhat of a separate entity from the spanning tree perspective. So basically, it's just we set up the Pacific Wave switches as the root, and then try and prevent that from changing in any other way. And then, in fact, some of the cases, the private VLANs were not running spanning tree on those at all because some of the issues that it runs into with some of the downstream devices that people are using.
So the downstream would be doing as like a transparent, or?
Yeah. So on the private VLANs, we're not.
Okay. No, go ahead. I'm just paraphrasing.
Yeah, on the private VLANs, we're not running spanning tree at all. So if anyone chooses, so basically the connectors are able to run whatever they decide to do transparently over those VLANs.
It's up to their discretion.
Exactly.
Okay. Thank you.
Okay, thanks very much, Dave.